Say you have 1 kilogram cork on one end of an antique scale and 1 kilogram of copper weight on the other end of the same scale. Since the cork displaces more air than the copper for the same weight, the upward force from the surrounding air on the cork would be greater since the cork has a greater surface area. If you see the scales in equilibrium, the actual mass of the cork will be greater than the mass of the copper. If you put the scale in a vacuum, the scale will tip over to the cork side because the upward buoyant force would have been removed. On the other hand, if you increase the air pressure to a higher than normal condition, the scales will tip over to the copper side of the weights. I realize this is all sort of confusing, but the relationship between density, buoyancy, pressure, surface area, and altitude all play a major role in the property of matter we know as weight. We think of weight as a constant rule, but when you really experiment with it, weight is sort of an arbitrary symptom of matter that can be altered at will using a bit of ingenuity and just changing some variables. A typical physicist will tell you the downward tendency of massive objects is obviously due to gravity. The massive Earth warping space-time, pushing down on the Earth and ultimately the apple, and the barometric pressure plays such a small role that it doesn't make much of a difference. My problem with that answer is the fact that the Earth isn't a spinning globe, so gravity doesn't theoretically need to exist, and so there must be another cause for this downward tendency of higher density objects. Furthermore, gravity has never been proven in the first place, so it's really just a theory which is only supported by the observation what goes up must come down. Since gravity as we understand it is a load of shrooms, we still need some force or tendency to dictate order or natural balance, where down is the place where higher density objects belong and up is the place where lower density objects belong. Gases and apples are not smart enough to navigate to their respective places in nature, but instead, nature is smart enough to naturally compel these objects to find their place of balance within the surrounding matrix or within the environment. I suspect that the density of the ground is resonating at a frequency which is closer to that of the apple versus the air surrounding it, and so the apple is attracted to the ground due to this principle. Similar vibrations. So if cooler, higher density gases are naturally compelled towards the ground, and hotter, less dense gases are compelled away from the ground, this is a natural response to an existing force that has nothing to do with gravity as we think of it. Our atmosphere not only increases our apparent weight on a scale, but the atmosphere we displace decreases our weight on a scale, and the atmosphere also dictates our terminal velocity, which is essentially a ratio between surface area and air density, a basic principle of aerodynamics or thrust versus drag. Now, if you're able to make a vacuum chamber 300 or 500 miles tall, then you might see an apple at rest that weighs a lot less, but that's just a theory. It's sort of irrelevant to the discussion, just an interesting hypothesis to make. I don't think they make vacuum chambers 500 miles tall. Anyways, since we know for sure the Earth isn't a spinning globe, to explain what goes up must come down, and instead of gravity as a warping of space-time, the natural balance forced upon inanimate objects appears to be related to objects having similar densities resonating at a similar harmonic frequency, and could theoretically be compelled to stick together or to be attracted to one another. Sonic frequencies can be visualized using cymatics, which is essentially a visual representation of a sound waveform. If sound waves can compel similar density objects, such as the powder in these examples, can compel them to adhere to a shape or a waveform, then we sort of have a precedent which demonstrates objects of similar density can be attracted to one another by applying different frequencies to the objects or material. If you study the Cavendish experiment, which was used to allegedly determine the so-called gravitational constant, and ultimately is extrapolated by extremely gullible people who are excellent at math to weigh the Earth and far-off stars, and even weigh clusters of galaxies, if you can believe that. Yeah, right.
One of my favourite scientists is Henry Cavendish. Even though he was part of the rich Dukes of Devonshire that family and incredibly rich. He went to Cambridge to study natural sciences, or natural philosophy as it's called, but he had a very curious condition in that he could hardly talk to anybody. So when it came to his Viva exam after 3 years of study, he fled Cambridge rather than sit in front of the examiners because he was petrified of them. But he was one of the most brilliant scientists of that 18th century in both chemistry and physics. For chemistry, he's noted because he analysed gases in the air. He discovered there was hydrogen, which is a huge component of the universe. He called it inflammable air. So he put some acids in a container, dropped some metal like zinc into hydrochloric acid, and got the gas to come off. And then to show it was inflammable, you could set light to it, he breathed it in and blew it into a candle. Now, do not do this at home because it blew up and took all the hairs off his face. He invented the idea of electric potential before everybody else and used to set electric currents through his body to work out the voltage was proportional to current, and he measured the current by the degree of agony he felt with the electrical current. This is not the normal sort of person.
Oh, Frederick, are you all right?
Yes. Would you excuse me for 1 minute, dear?
Oh, of course, Doctor.
Igor? May I speak to you for a moment?
Of course.
Sit down, won't you?
Thank you.
No, up here.
Oh, thank you.
Now, that brain that you gave me, was it Hans Delbrück's?
No.
Ah, good. Would you mind telling me whose brain I did put in?
And you won't be angry?
I will not be angry.
Abby someone.
Abby someone. Abby who?
Abby Normal.
Abby Normal.
I'm almost sure that was the name.
Are you saying that I put an abnormal brain into a 7.5-foot long, 54-inch wide gorilla? Is that what you're telling me? Quick, get him up!
What? 3 syllables, yes?
I wonder who that could be at this time.
The current by the degree of agony he felt with the electrical current. This is not the normal sort of person. He couldn't talk to most people. He couldn't talk to women at all. His housekeeper would get a recipe for something or other, and he'd say, no, lamb tonight, leg of lamb, and leave a note for her. He wouldn't say it, he'd write it. He would dine in the evening with his friends, and he would talk to them, but if he didn't know somebody, and you wanted to ask him a question, apparently you had to go to the Royal Society and he would be in the room and you'd address the room this question about physics and you postulate, and if he felt in the mood he would reply to the room. He was a very strange man, and yet he's absolutely wonderful. He invented hydrogen. People went up in hydrogen balloons and could see the world from, through that perspective. He did most of the experiments quietly on his own, keeping his notebooks, and it was only after his death and a persuasive campaign by Clerk Maxwell, the famous Maxwell of Maxwell's equations from Cambridge University, that he actually got the notebooks from the estate of the Dukes of Devonshire and discovered after the event that Cavendish had discovered the unit of capacitance, discovered dielectric constants, he discovered Dalton's law of partial pressures, he discovered or written about Coulomb's law, all before these guys had done it and just left it unpublished in his notebooks. Towards the end of his life, he did a crucial experiment, which is represented by these lead balls. He lived in Clapham Common, which is nowadays a very poor part of London, but there it was quite fashionable. And he built his own place. His library he built somewhere else because he didn't want anybody borrowing his books from his house. Otherwise, he would have to ask the book back and he didn't want to talk to them. So his library was 4 miles away. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had 2 lead balls, like this, suspended from the ceiling. Only this is not to scale. This is, I mean, lead balls. Now, the real problem is that he wanted to measure the attraction between 2 objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball. So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he looked through, and he put a telescope out there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one. And so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way. And the wire would twist, and as the wire twists, the mirror, which is dangling in there, would twist a little bit, and light which comes in would be reflected off at a slightly different angle. And all he had to do was measure the angle. He then had to move it the other way round. Oh, he didn't move this bit. He moved the lead balls round so that you had an equal and opposite effect on the other side. So instead of having, you'd have that configuration. He had this is a very complicated technical thing for the time. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics, and a lot of chemistry.
So setting